A single server processing 20 requests a second is a quiet, predictable operation. An architecture supporting 1 million connections is a volatile, distributed organism. We define scalability strictly as a system's capacity to handle increased load without degrading performance or failing. When demand spikes, the system must absorb the pressure. Historically, the instinctive solution to increase demand is vertical scaling. This means adding raw compute power, upgrading the CPU, expanding the RAM, or swapping in faster hard drives on a single machine. The alternative is horizontal scaling. Instead of upgrading one machine, you add entirely new, parallel machines to the network, dividing the incoming traffic across a fleet of computers. Vertical scaling is simple. The codebase remains the same. Horizontal scaling forces the software to manage distributed operations over a network, introducing technical hurdles that a single machine never faces. However, physical hardware has limits. To reach true scale, handling millions of active users, engineers must abandon the simplicity of a single powerful machine and build a horizontally decoupled architecture. This diagram illustrates a baseline monolithic architecture. User traffic flows directly into a single web server, which reads and writes to a single attached database. For low-volume traffic, this works perfectly. Watch what happens when traffic surges. The single server processes every incoming packet sequentially. Very quickly, the CPU and memory hit total utilization. The operational bottleneck is absolute. Because the hardware cannot process the queue fast enough, new requests time out. The system drops connections, and the application goes offline. At this stage, you could buy a server with double the RAM, but high-end hardware gets exponentially more expensive, and eventually the largest commercial server on the market will still fail under millions of requests. Because vertical scaling inevitably hits a hard physical and financial wall, distributing the load horizontally across multiple cheaper machines becomes a mathematical necessity. Adding a second server immediately breaks a traditional monolithic application. If a user logs in to server A, active session data is stored locally in memory. If their next click routes them to server B, the system will not recognize them. This requires the first major architectural shift: stateless services. All local session state must be externalized. The memory of who is logged in is moved off the individual web servers and into a shared, centralized storage location. By externalizing the state, the web servers become interchangeable. Any server can process any request from any user by quickly querying the shared session storage to get the required context. We solve this by pairing our horizontal scaling with a load balancer. It acts as an intelligent traffic cop. It sits in front of the web tier, evaluates the health of every server, and routes incoming packets to ensure no single node is overwhelmed. Because session state is no longer trapped on local hardware, the load balancer is free to distribute traffic to any available node, scaling indefinitely. The web tier is now horizontally scaled and highly available. But those web servers are generating massive amounts of queries, routing them all to a single database. The disk I/O wait times skyrocket, creating a new critical bottleneck. To protect the database, we introduce caching, typically using memory stores like Redis, to intercept frequent read requests. Because cache memory operates vastly faster than traditional database disks, serving data directly from this intermediate layer bypasses the database entirely. Latency drops to milliseconds. Managing a cache requires strict parameters. Time to live, or TTL, dictates how long data stays in the cache before it expires. The trade-off is clear. You must balance data freshness against your cache hit rate. Dynamic user data requires a short TTL to prevent serving outdated information. Static content, like a site logo or structural formatting, takes a long TTL to maximize the hit rate and minimize database queries. The cache absorbs the read traffic. However, heavy write operations, users uploading files or generating complex new entries, will still lock up the primary database. We resolve this through database optimization, specifically read replicas. We physically separate the traffic. All write operations route to a single primary database, which then constantly copies its data down to multiple replica databases that handle all the read requests. Synchronous task holds the server thread open, preventing it from accepting new users. We break this synchronous dependency with asynchronous processing via message queues. When a user requests a heavy task, the web server does not process it. It drops the task into a queue and immediately sends a processing message back to the user. Dropping the payload into a message broker like Kafka instantly frees the web server thread. The server goes right back to routing light, fast web traffic. Behind the queue, we deploy independent background worker nodes. These nodes pull complex tasks from the queue at their own pace, do the heavy computation, and update the database when finished. This architecture strictly isolates the computational heavy lifting. The long-running tasks are handled entirely out of sight of the main web tier. Asynchronous processing ensures that one user's computationally expensive request cannot paralyze the web servers for everyone else, maintaining the illusion of instant speed across the platform. We have successfully scaled the monolithic application, but a massive, unified codebase carries a structural risk. A single memory leak in the billing module can crash the entire application, taking down user logging and video playback with it. We mitigate this risk by fracturing the monolith into microservices. The application is divided into distinct, isolated operational domains, each functioning as an independent application with its own database. This isolation means if the video processing service fails, the billing service stays online. Furthermore, engineering teams can deploy updates and scale specific features independently based on targeted demand. Splitting the databases across microservices forces a crucial decision regarding data integrity: strong consistency versus eventual consistency. A banking application requires strong consistency. An account balance must be strictly verified across all services before proceeding. A social media feed tolerates eventual consistency. It is entirely acceptable if a new post takes a few seconds to populate across all regional servers. With our services isolated, we apply the ultimate layer of dynamic resource management: autoscaling. Autoscaling rules monitor real-time load metrics, like CPU utilization. When traffic spikes, the system autonomously provisions and boots up new server nodes. When traffic subsides, it destroys them to save costs. Microservices and autoscaling strip away the rigid, static nature of early architectures. The system becomes a living, elastic entity, capable of dynamic adjustment and self-healing. This is the resulting architecture. From a single vulnerable server to a globally distributed, elastic network capable of processing 1 million concurrent users. This scale was achieved entirely through aggressive decoupling. We separated state from the web servers, read operations from write operations, and synchronous requests from asynchronous heavy lifting. But look at the operational reality. Every single component added to bypass a physical bottleneck introduced a new layer of network latency, deployment difficulty, and engineering overhead. Scale requires sacrifice. You trade the simplicity of a single server for the infinite ceiling of horizontal scaling. You trade immediate data freshness for high cache hit rates. You trade strong data consistency for high availability across microservices. There are no universally correct system designs. There are only optimized trade-offs based strictly on the mathematical requirements of your specific application. Blindly applying heavy architectures like microservices or massive message queues to a low-traffic application is premature optimization. It guarantees high costs and slows down development for scale you do not possess. Success in system design comes from identifying your hardware limits and choosing the specific architectural bottlenecks you are willing to manage.